So thanks everyone for coming, and thanks to the other organizers for inviting me to speak. So I'll start by telling you what perfect difference sets are. So a subset of a finite cyclic group is a perfect difference set if every non-zero element of the cyclic group can be written uniquely as the difference of two elements of D. Every All right, so for example, the set 1, 2, 4 in the integers mod 7 is a perfect difference set. So we care about these sets in additive number theory because they're examples of large CDOM sets. These are large CDOM sets. CDOM set is a subset of an abelian group with no non-trivial additive quadruples. So that means that if A plus B equals C plus D, for A, B, C, and little d, big D, then A and B have to be C and D. So in additive number theory, we care a lot about the existence of large CDOM sets. So we care about perfect difference sets. So these perfect difference sets, they can't exist in every cyclic group, just for counting reasons. So for such a D to possibly exist, we need M to be of the form n squared plus n plus 1 for some integer n. And then the size of D would then have to be n plus 1. In this situation, we say that n is the order of the perfect difference set. And this terminology mirrors the terminology from the study of finite projective planes. And there's good reason for that, which is that any perfect difference set gives rise to a finite projective plane. So if D is a perfect difference set, order n, we can get a projective plane of order n by taking the set of points to be the integers mod n squared plus n plus 1. And hopefully people can see this, if they can. And set of lines to be the set of translates. A plus D of D. Right, so in addition to us caring about these perfect difference sets in additive number theory, people in design theory and finite geometry, and also turns out computer science care a lot about them. So the kind of fundamental question about them is, when do they exist? So let's say for which n do perfect difference sets of order n exist. So in 1938, Singer constructed examples of perfect difference sets of all prime power orders. So perfect difference sets of power order, I should say all prime power orders exist. And the construction is pretty easy. So we just take zeta to be, or first we'll take, say, Q to be our prime power. We take zeta to be a generator of the multiplicative group of FP cubed. Then the set of D of element, or the set D of K such that zeta to the K has the form 1 plus A zeta for A and FP, F cubed, sorry. So yeah, this should be a cube. Along 0, then reduced mod q squared plus q plus 1 is a perfect difference set. And this, the perfect difference setness of this set just follows from the fact that zeta has to be a root of a irreducible cubic. Okay, so it's an old conjecture that actually these are the only orders for which perfect difference sets exist. That is, every order of a perfect difference set is a prime power. And this is known as the prime power conjecture. It goes back to the 40s. I couldn't find the definitive, like, earliest, like, paper in the 40s where it's mentioned. So n is the order of a perfect difference set. And is a prime power. So this conjecture has been verified for all n below 20 billion. 20 times 9 by Gordon. And yes, a paper that just came out this summer, beating his previous record with Baumert, I think from maybe almost 2 decades ago, of 2 billion.
And are all these of order Q supposed to be the kind you wrote on the board?
So that's a conjecture of Singer. And I think that's only been checked up to maybe 100. I'll say a little bit more about that later. So there's also a more general conjecture that all finite projective planes have prime power order. It's also conjectured that all finite planes but in contrast to where we know the prime power conjecture for perfect difference sets up to 20 billion, we still don't know whether there exists a projective plane of order 12.
Why is that numerically so hard to check? Do you know?
I don't know. I think so.
Well,
I think even checking if there was one of order 10 was some sort of like massive,
it's
like,
also,
like crazy thing that needed kind of a lot of its own theory. And I don't kind of know any of it.
I think potentially you have 2 to the 157 possibilities.
yeah, I was hoping that you wouldn't have to go through all of them. To do something clever first.
Yeah, I remember when Lamb did it, and the one of order 10 she's saying, and that was like a 4-year calculation or something. Even being clever.
Okay, so there's so this prime power conjecture is like really hard, and it seems to be out of reach. And kind of the strongest results towards it, like those that eliminate the most possible orders of perfect difference sets, just kind of remove all or almost all of the integers in some congruence class. So I'll give you, I guess I'll give you like kind of all 3 of these results. So the first is due to Ruck and Reiser from, I think, 1949. And this is actually about kind of more general projective planes. And I think it's actually the only kind of general non-existence result for projective planes. So it says that we let, if n is congruent to 1 or 2 on 4, and n is the order of a perfect difference set, then n must be able to be written as the sum of 2 squares. Okay, so the density of integers are the sum of 2 squares. It's like a constant times n over square root log n. So this removes most of the elements that are congruent to 1 or 2 mod 4. Oh no, this should be some more general than perfect difference set. It's like I said, this is any order of projective plane. So this makes it easy to check that there's no projective plane of like order 6. And the next 2 I'll tell you about are just for perfect difference sets. Here's a result of Numerical, letter from, I think, 1984, says that if 2 is an even integer and it's the order of a perfect difference set, then either n equals 2, n equals 4, or 8 divides n. And there's also one mod 9 like this due to Wilbrink. Says that if n is multiple of 3 and is the order of a perfect difference set, then either n is 3 or n is multiple of 9. So this is it for these sorts of results. So in particular, there's no condition mod like any power of 5 that anyone's found yet. These just remove kind of a positive, but not one density of possible orders of perfect difference sets. So there are no results in the literature that say even that the possible orders of perfect difference sets has density 0 in the integers. So the result I'll tell you about today says that not only is a set of orders of perfect difference sets a set of density 0 in the integers, but actually has the density predicted by the prime power conjecture. So we have that the number little n, little big N, such that little n is the order of a perfect difference set is asymptotically n over log n. Asymptotically the same as the number of prime powers below n. So I can get kind of an explicit thing for this little of 1. The little of 1 that I get, I didn't try that hard to optimize this, is like e2 minus a constant times log n divided by log n.
Please don't improve that, because the most logs I've ever seen in my life.
Do you practice writing that to get it
Um,
lying so well?
no. But I love writing it.
How many on the top and how many at the bottom? I hope you haven't got the same number.
No. It's 5 on the top, 6 on the bottom.
And is the constancy effective?
Yeah, it's probably like 10 or something. Okay. So before I start talking about what goes into this proof, I want to come back to this question of whether these examples of Singer are the only ones for prime powers. so Singer, in his original paper on this stuff.
Actually, I have a question about the theorem. Does the theorem actually know about the existence of these Singer examples, or is it completely independent?
Oh, sorry, what?
You're counting the number.
Oh, yeah. So I get the upper bound.
Right, but in your proof, at any moment, do the Singer examples enter, or they're just invisible?
So
In other words, there are that many. You said the asymptotics is correct with the conjecture.
yeah.
So what you're showing is the number of exceptions to the conjecture is small.
Yeah.
But do you ever, in the proof, well, I could wait to see, but do you ever actually, these things are constructed by cyclotomic polynomials. Does that enter that construction into your proof?
No.
Okay. So
At some point, I'm like, okay, I just want to bound the number of things with at least like 2 different prime factors.
okay.
And I use that it has like maybe a prime factor below like little n would have a prime factor below like square root n.
Okay, so my question was, you're just counting?
Yeah, I'm just counting.
Okay.
So Singer, in his original work on this stuff, so he conjectured that all perfect difference sets of prime power order are given by this construction. Then I'll add maybe up to translation just to be safe. So if you combine this with the prime power conjecture, then you get a complete classification of all perfect difference sets. So this prime power conjecture classifies perfect difference sets and so such a result would answer a very special case of kind of an important question in additive number theory, which is like, what do large Cedan sets look like? So this is basically kind of as precise as I think anyone can like phrase this question, because no one really has any idea what the answer is. Or maybe we can be a little more precise. So the kind of largest examples, Cedan set, like the largest examples of Cedan sets that we know come from algebraic constructions. So in particular, you can't construct kind of the largest things using some like random construction. So random doesn't do as well. So there are kind of a lot of kind of different algebraic constructions. Like there's this Singer one, and if you want one like in the integers, one way to get a large Cedan set is to take the graph of a quadratic in the integers mod p cross integers mod p, and then project it down to the integers. So these give the largest examples we know, and then the question is, do all large Cedan sets look kind of algebraic in some way? And yeah, so I think this is a thing that we can't be more precise about asking. And so if one were to prove the prime power conjecture and then this conjecture of Singer, one would at least know the answer to this question in some like very special case.
So how big can you make the by random? You get the size to the quarter, or?
Maybe like a third. So I think that's all I have to say before I start talking about the proof. Does anyone have more questions? So what goes into the proof? So the starting point is two existence criterions. Criteria or perfect difference sets that say that certain relations between the prime factors of n and the prime factors of n squared plus n plus 1 must hold. So two existence criteria for perfect difference sets giving relationships between the factors of n and n squared plus n plus 1. Okay, so then once you have these two existence criteria, then this just turns into like an analytic number theory problem. And the problem is, in what situations do you apply these different existence criteria? Like, how do you chop up the set of little n? So the first one, an old theorem of Man from 1952. So it says that we let n not be a perfect square and be order of a perfect difference set. Then if P is prime dividing n, and Q is a prime dividing n squared plus n plus 1. And now for the remainder of my talk, P and Q are always primes. Then you must have that P is a quadratic residue mod Q. So we get a lot of mileage out of this, right? So just this is enough to prove that the number of orders of perfect difference sets has the correct order of magnitude. But this isn't enough to get the asymptotic result. The reason is that this condition is empty when n squared plus n plus 1 is a prime that's 1 mod 4. So this is unfortunately useless when n squared plus n plus 1 and that's 1 mod 4. Okay. So why is this? It's basically just quadratic reciprocity. So if P is a prime dividing n, then we definitely have that n squared plus n plus 1, quadratic residue mod P. And when this is a prime that's 1 mod 4, P must be a quadratic residue mod n squared plus n plus 1. So this conclusion like always holds. So this is of no help in showing that the number of n, such that n squared plus n plus 1 is 1 mod 4 and is prime, and its order of perfect difference set is a little low if n over log n. We have to deal with this case because we expect that this happens like a constant times log n of the time. So we have to deal with this. Since minus 1 mod 4. I'm not claiming this. So since we expect that, and it's like in a solving problem to show something like this, that n squared plus n plus 1 is a prime that's 1 mod 4. Like n over log n all the time, or little n below big N. Okay.
Are you going to say a word about Mann's theorem? Is that something we just take as a black box?
Yeah, you should just take it as a black box because.
Is it hard?
Not really if you know like the multiplier theory of perfect difference sets. But so I would rather talk about like number theory and tell you guys about that. So
Okay.
oh, sorry, what?
Fair enough. No, I just was wondering where it's coming from. But you say it's non. It sounds non-trivial.
Yeah. So I think just the idea of these multiplier things is the really non-trivial part. So multipliers are basically elements of the multiplicative group of like the integers mod n squared plus n plus 1, such that when you multiply every element of a perfect difference set by them, you get just a translate of that perfect difference set back. And okay, so I guess it's clear that these are like a group, but it's like highly non-trivial that this group like actually has anything in it besides just one. And it's also non-trivial to show that actually there's some translate of your perfect difference set that's fixed by all these multipliers. So it turns out that your perfect difference set is just like an orbit under this group of multipliers, and then
Okay, it sounds like it's the structure of the abelian group, the multiplicative group coupled with combinatorics.
Yeah.
Okay.
So this result of Mann like kind of isn't enough to deal with this case when n squared plus n plus 1 is a prime that's 1 mod 4, which we have to deal with. So I had to prove another existence criterion just for this case, which is like Mann's theorem, kind of a not very difficult consequence of the theory of multipliers, like whatever this is. And it says that let's assume we're in exactly this situation. So Q is some prime of the form n squared plus n plus 1. And it's congruent to 1 mod 4. And then if P is any prime dividing n, then P must be a quartic residue. Mod Q. So this looks, I guess, superficially similar to Mann's criterion, but so it turns out that in contrast to Mann's criterion, there isn't any like positive density subset of the n such that n squared plus n plus 1 is a prime plus 1 mod 4, such that this conclusion is empty. So we can actually use it. Okay, so now that I've told you these two kind of existence results, I think it should be, or you should be like pretty convinced that this asymptotic version of prime power conjecture that I wrote down is true, because typically like n or n squared plus n plus 1 should have enough prime factors that like these should be like really like hard to like satisfy most of the time. But the problem with making this heuristic like into a proof is that like n squared plus n plus 1 depends on n. So n and n squared plus n plus 1 are just two like random integers of size like n or n squared. So you have to deal with this dependence. So the kind of central idea that I use over and over again to get around this is to just kind of use a union bound in kind of several places to remove the dependence of, say, most of the prime factors of n squared plus n plus 1 on some small factors n. And then, so you lose a little by doing this union bound thing, but the amount that you gain from the strength of that theorem and like this lemma combined with like some sieving, like more than makes up for what you lose by using the union bound. So we can make up for losses coming from the union bound. So this is really vague, like probably confusing, but to rectify that, I'll tell you in more detail, like how that's done. So to argue, you split up n based on the number of prime factors of n squared plus n plus 1. And kind of use a different strategy in each of these cases. So we split up based on factors of n squared. So the most straightforward situation is when n squared plus n plus 1 has at least 3 prime factors. And then the second most straightforward case is when n squared plus n plus 1 is the product of 2 primes. And kind of the most involved is when n squared plus n plus 1 is prime. so what goes into the case when n squared plus n plus 1 is at least 3 prime factors. So so in this situation, typical such n such that n is the order of perfect difference set, n must have like 2 kind of smallish prime factors, neither of which are 3. And then the number of n that don't have this property, they can be, the size or the number of them can be bounded in like a similar way to what I'm about to sketch. So for a typical such n, there exists 2 distinct primes, p1 and p2, that aren't 3. And we also want them to be smaller than like the 1 over 100 or something, such that p1 and p2 divide n. And then for all such n, we also have always some prime q below n to the 2/3 that divides n squared plus n plus 1. Okay, so then right, the idea is to just split out based on this p1 and p2 and q, and then bound each of the individual sets in sum. So this is the union bound part of it. So then just need to bound such that n is the order of a different set. Okay, now we apply Mann's theorem. Oh, maybe I erased it. So Mann's theorem says that it's found above by sum over the same thing. And again. Such that if p prime is a prime dividing n, and p prime has to be quadratic residue mod q. And if, say, q prime divides n squared plus n plus 1, then p1 and p2 have to be quadratic residues mod q prime. And then kind of the critical observation is that bounding the size of these sets is a sieve problem of dimension 5/4. And 5/4 is greater than 1. So we win a lot more than we lost from the union bound. So bounding the size of this is a sieve problem of dimension 5/4, because this condition removes like half a congruence class modulo each prime on average, and this one removes like 3/4 modulo each prime on average. So this whole thing is bounded above by sum over, same thing as before. And over, again, 5/4 times some kind of arithmetic factor, depending on P1, Q and Q, divided by P1 times P2 times Q. So this kind of arithmetic thing, just some like product of like partial Euler products of some Dirichlet L functions depending on P1, P2, and Q, is like really small on average. So we only lose like some bounded power of log by summing. So this ends up being n over n to the 5/4 times some logs. So that's how the situation when n squared plus n plus 1 has at least 3 prime factors goes. It's really straightforward. Okay, so when n squared plus n plus 1 is the product of 2 primes, you have to split into some subcases depending on the size of the smaller prime. So we'll assume that Q1 is less than Q2. So there's 3 subcases. The first is when Q1 is below like n divided by log n to the 100, then basically what I just did, some modification of it works. And Q is between n divided by log n to the 100 and let's say n divided by log n to the 1/2. We need to do something more delicate. Need to argument is still based on splitting up the little n below big N in some way, applying Mann's theorem, and then using a sieve to bound something and saving a little bit. So let's see more about that. Then the final case, or subcase, is when this Q1 is between n divided square root of log n and n. And then this strategy of using like Mann's theorem and then some sieve stops working. You can't go all the way up to n because then you kind of lose any space for the sieve to save you anything. And then the idea here is to forget is a big difference set kind of condition. And just show that there are ends up being constant times n to the log n, or n divided by log n to the 3/2, many n below n, such that n squared plus n plus 1 is the product of 2 primes with Q1 bigger than n divided by square root of log n. And the way this is done is by using an enveloping sieve. Enveloping sieve argument. And so the enveloping sieve argument is pretty standard as far as like enveloping sieve arguments go. Kind of the only real new input I needed was I needed an asymptotic count, the power saving error term of the number of integer points on the hyperboloid y squared minus 4xv equals -3 with various size and congruence restrictions on x and z.
Upper bound, right?
So actually you need an asymptotic count to be able to use an enveloping sieve for like this input, but then the enveloping sieve just gives an upper bound for like the number of these that can be written as the product of 2 primes.
By the way, I think you've answered my other question, my first question, whether you use those examples. I mean, the prime case is gives the main term, right?
Yeah.
And the prime case is a half-dimensional sieve of Ivanich, probably. I don't know if you're using that, but you have to get the asymptotics there, not with the right constant.
Oh,
No?
well, Singer already gave like the lower bound.
Oh, so you use it?
Yeah.
Okay, all right. Then we're going to close the circle. Okay, good.
So this is how you deal with when n squared plus n plus 1 is the product of 2 primes. And then this is my little remaining time. I'll say something about the hardest case. So when n squared plus n plus 1 is prime. This actually contains the easiest subcase, which is when n squared plus n plus 1 is the prime that's 3 mod 4. Then this case is easy for the reason that when it's 1 mod 4, it's hard. So by a similar like quadratic reciprocity short argument, it turns out that any n such that n squared plus n plus 1 is a prime that's 3 mod 4, and n is the order of perfect difference set, must satisfy the condition that all of its prime factors are 1 mod 4. So then you're basically just, you can upper bound by the number of n such that n squared plus n plus 1 is a prime, and n is only divisible by primes that are 1 mod 4. So then you get a bound of n divided by like log n to the 3 halves. So that's easy. And then the hardest case is when n squared plus n plus 1 is 1 mod 4. And the idea for this case is, so you split the n of base on the smallest k for some k going to infinity like really slowly with n. Factors, column p1 up to pk. So then for n to possibly be, so for n with these being as small as k prime factors, actually I want these all to be below log n. So this step is where all the logs come from, like these 11 logs. So then for such n that have p1 up to pk's, there are smallest k prime factors. Oh, and the ones that don't have this many small prime factors below log n, you can show that the number is like negligible. So then you need that each one of p1 up to pk are quartic residues modulo n squared plus n plus 1. So we'll need number of n such that n squared plus n plus 1 is prime incongruent to 1 mod 4. And satisfying that all these pi are quartic residues, and that 1 up to k are smallest factors, and then using quartic reciprocity, you can turn this condition into n squared plus n plus 1, being able to be written as a sum of two squares, one of which satisfies some congruence conditions depending on T1 up to PK. And then you can bound the number of prime n squared plus n plus 1 that can be written in this form, basically by using the Selberg sieve, as long as you have an asymptotic count with power saving error term for the number of integer points on a different hyperboloid than the one I wrote before. So I need asymptotic count with power saving error term.
By the way, you didn't say how you counted the number of points on a.
Oh yeah.
There are many
So I'll say
ways.
that.
I'm curious which way you used.
The way I did it is I adapted like an old argument of Hooley that he used to count the number of divisors of values of quadratic polynomials. But I didn't really need that much like uniformity in various parameters, and I just needed some power savings. So I assumed like some automorphic forms person could prove like kind of a stronger one of these counts.
Mm-hmm.
But this Hooley was quick.
Yeah, but you can get a power saving, you know that.
Yeah, yeah. So the hyperboloid I had to count points on this time was like 4x squared plus 16y squared minus b squared equals, I think, 3. And then I needed size and congruence restrictions on y and z. Oh no, I'm writing in the bad zone. Probably no one can read this, but I just wrote what I just said. So counting these points on this hyperboloid was like a huge pain because it's not as nice as this other one, but still this Hooley argument works. Okay, so I think I'm done.
Are there any question to the speaker?
She finished very, Sarah, you finished very quickly. I was going to ask.
Oh.
If you improve, I mean, I love your mini logs, but let's say we want to improve it. So this integer count on the hyperboloid, we're using Hooley's methods. They're much weaker than automorphic methods, which
Yeah.
can give power saving and quite transformative. So would that, I mean, there's no interest in doing, if all you want to get is this main term, but if you want to improve that, I don't know where's your main obstacle for getting rid of all those logs?
So kind of improving the point counting, I think would only maybe save you like a constant factor somewhere. The biggest obstacle is this thing I do where I split up n based on the smallest k prime factors below log, log, log. So I need k to go to infinity like really slowly to make sure that the ones that don't have k many prime factors below log 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 are actually smaller than my main term. So it's in that mess. And I needed log log log, so I did log log, then like some bound ends up being like too big.
And the Vanet's half-dimensional sieve, are you familiar with that? I mean, he has an asymptotics for half-dimensional sieves, if I remember.
Yeah.
That's not good enough?
Yeah, so I thought about this when I was working on it. I think I ended up, I think I just couldn't get a good enough error term. And that was my problem. Yeah, I did think about the like half-dimensional sieve and then ended up doing this point counting thing instead.
Okay, yeah, because his is a purely half-dimensional sieve. If you want to count the number of primes in a quadratic upper bound with, you're not going to produce primes, right? But in terms of the sieve, the asymptotics in the sieve, that's quite powerful.
Mm.
Okay. Thank you.
Are there more questions?
Yeah, I was just trying to think about how you might generalize this. I mean, you have prime factors of 2 forms in N with some relation.
Mm.
I mean, I don't know if there's anything sensible one could do. Some of it reminds me of a sort of large sieve generalizations to 2 dimensions. I don't know if you thought about any lines like that.
I did think about that and could not make like anything work. Yeah, that was like my original approach to thinking about this. Like, oh, there must be some sort of like 2-dimensional way to sieve, but nothing I could do worked.
Yeah, it's not clear what framework. With the things that people have done have been fairly simple. This is clearly not.
Okay, do we have more questions? So let us thank Sarah again.